Welcome to Maths with EJD. We're talking about coordinate geometry and conic sections, and then focus now on hyperbola. And we already saw that conic sections are formed when a cone intersects a plane. So if you have a cone, okay, guess I can demonstrate that on the next page. So imagine that you have, okay. Is this what I want to do? Okay, let me use this. So imagine that you have a cone like this. So if you cut the cone vertically, then you get a circle, right? That's a circle. But then if you tilt it a bit, if you then tilt that, then you get an ellipse. So this is circle. Then this is ellipse. Then if you tilt again, then you get a, so it doesn't cut through fully anymore. So you get a parabola. I mean, I'm not doing justice to this thing, but I mean, you can imagine what I mean. So you have, that's not looking good. Let me try again. So you have a parabola. And then if you go further, then you have a hyperbola. That's not looking pretty good. Uh, Let me try once more. However, it comes to take it like that. So it's all about tilting the angle, and then you have hyperbola. So you have hyperbola, and that's how the whole thing goes. Hmm. So, we've treated circles in the past, we treated circles in the past, different things about circle, 3 videos on that. Then I took care of a parabola. Okay. So I took care of parabola. So we talked about parabola, then I've done ellipse. Now the focus shifts to hyperbola. So now that we are talking about hyperbola, let's see what we need to learn about that. So here now, a hyperbola is a type of conic section formed when a plane cuts both naps of a double cone. Okay, like what we saw there. So it is defined as the locus of all points in a plane, such that difference of their distances from two fixed points called foci is constant. So for parabola, it was the sum of their distances, but now it is difference of their distances. So a hyperbola is just like a parabola, except that instead of sum, you have difference, basically. So if you look at the equation here, for ellipse, sorry, for ellipse, it is to be x squared over a squared minus y squared over b squared. I mean, plus y squared over b squared. For hyperbola, it is minus, basically. So it is defined as the locus of all points in a plane, so that the difference of the distance from two fixed points called foci is constant. So if the fixed points are f1 and f2, and any points p of x comma p x comma y on the curve satisfies pf1 minus pf2 equals 2a, then the locus of all such points p is called hyperbola. So the locus of all points x comma y is called the hyperbola. Now we'll talk about the standard equation of a hyperbola. So first of all, we have the transverse axis along the x-axis. That is x squared over a squared minus y squared over b squared equals 1. We assume the center is at 0. It doesn't have to be there. It can be at any other point. So if it says at any other point a, b, or hk, so you have x minus h squared, then y minus b squared, replacing x squared, y squared here. Then the vertices are plus or minus a comma 0, and then the foci plus or minus c comma 0, just like ellipse, where c squared is a squared plus b squared. For ellipse, c squared was a squared minus b squared. But here it is c squared equals a squared plus b squared. Then you have the transverse axis length 2a, conjugate axis length 2b. So for y-axis, you just have things switching over. So instead of having x squared over a squared, you now have y squared over a squared minus x squared over b squared. So if you're switching axis for ellipse, you just switch over the a squared and b squared. But in this case, you switch over the y squared and x squared because now we are subtracting. So the a squared and b squared remain where they are, but the y squared and x squared will switch places if you for you to change axis. So we demonstrate all that. So we also assume the center is 0. The vertex now will be 0, comma plus or minus a, and the foci 0, comma plus or minus c, where c squared is equal to a squared plus b squared. Okay. Then we talk about foci and eccentricity. So first of all, talking about foci, so uh that's talking about focuses now, if you like to put it that way. So for x squared over a squared minus y squared over b squared equals 1, the foci are plus or minus c comma 0, which we saw up there. And for y squared over a squared minus x squared over b squared equals 1, the foci are 0, comma plus or minus c. And the relationship between a, b, c will be c equals square root of a squared plus b squared, unlike square root of a squared minus b squared for ellipse. And then for the eccentricity E of a hyperbola is given by E equals C over A. And since we know that C is square root of A squared plus B squared over A, right? So we can extend the square root. So we have square root of A squared plus B squared all over square root of A squared also. I mean, I think I can, let me demonstrate that. So what we mean is that we already know the eccentricity is C over A. And then we know that C is square root of A squared plus B squared, all over A now. So this is the same thing as square root of A squared plus B squared all over square root of A squared, and then that means the eccentricity can then be square root of A squared plus B squared all over A squared. So that means E is square root of A squared over A squared plus B squared over A squared. So meaning that the eccentricity can simply just be square root of 1 plus B squared over A squared. That's eccentricity expressed like that. And that's why we have this. And then, of course, the E has got to be greater than 1. In the other case, in the case of ellipse, the E is between 0 and 1. But for hyperbola, that's why it's hyper. Hyperbola, the eccentricity is E is greater than 1 in this case. So a hyperbola always has an eccentricity greater than 1. So that's why it's a hyperbola. Then we have asymptotes. So the asymptotes of a hyperbola are straight lines that the hyperbola approaches but never meets. Okay? So for the one about the x-axis, you have x squared over a squared minus y squared over b squared equals 1. So the asymptote will be y equals plus or minus b over a, all right? B over ax. Therefore, y squared over a squared minus x squared over b squared about the y-axis, the equals 1, right? The asymptote will be y equals plus or minus a over b x. So you just switch over the a and b, basically, and you get it for the other axis. That's the asymptote, okay? So we demonstrate all of this. So yeah, using the Python code now, imagine that A is 3. By the way, what is A again? A is so okay, the transverse axis length. A is half of the transverse axis length. B is the half of the conjugate axis length. Okay, so that's A is 3, B is 2. Then you generate valid X values for both branches. So you have X right, X left, and all that. So A to 10 minus 10 to minus A, all that. Compute corresponding Y values using the necessary formula, and then plot both branches, plot the asymptotes, then do the axis formatting. So with all that now, we can see the things we've been talking about. So we have the code running here. Now we have it, okay? So you see, this is a hyperbola. So in this case now, there's eccentricity here. So you have hyperbola, the right branch. You have the right branch here. This is the left branch. And then you have the asymptotes. The lines that just, the hyperbola tries to reach but never reaches, which is plus or minus b over ax, like we saw up there. So let's take our first example. It says, find the equation of the hyperbola with foci at plus or minus 13, comma 0, and transverse axis length at 24. So in this case now, it tells us that 2a equals 24 because that's the transverse axis length. So a is 12 and c is 13. That's talking about the foci now. So c is 13. So from c squared equals d squared plus b squared, we can easily get the b because we weren't given that. That's the conjugate axis length, I believe. So b squared now is equal to c squared minus a squared. That's 13 squared minus this. And we have 25. So b squared is actually 25. That means b is 5. So hence the equation of the parabola, of the hyperbola rather, is x squared over 144 minus y squared over 25. Okay, let's see that. Using Desmos, x squared, x raised to the power 2 divided by 144 minus y raised to the power 2 divided by 25, I think, divided by 25, yes. And that is equal to, all of that is equal to 1. Okay. Something wrong? X squared over 144 minus y squared over 25 equals 1. Oh, what's wrong? Okay, let me go again. X raised to power 2 divided by 144 minus y raised to power 2 divided by 25 equals 1. Ah, okay, it was there all this while. Sorry, except that it was far away. So this is it. It was there all the while. So, and then we know the uh, what is it called now? We know the asymptotes that it is equal to y equals b over a, right? That's 5 over 7. It will square root. I mean 5 over 12, then x. So you can see that as one asymptote right there. Then all we just need to do is take the negative of the same thing and we get the second asymptote. Okay, so minus and you get the second asymptote like that. So that's how that works. So that goes. Example 2, find the coordinates of the foci of the vertices and equations of the asymptotes of x squared over 9 minus y squared over 16 equals 1. So in this case, of course, to get a now, a squared is equal to 9, so a is 3, b squared is 16, so b is 4, right? Now you compute c. So c now is c squared equal, to get c squared is a squared plus b squared, and that's 9 plus 16, which is 25. So that means c is 5. So what we need is the coordinates of the foci, vertices, and equations of the asymptotes of that expression. So of course here we see the center is 0, 0 because we have x squared, not x minus something squared. So the center is 0, 0. Same for y. It's y squared, not y minus something squared. And the vertices are plus or minus 3, comma 0. That's plus or minus a. And the foci are plus or minus 5, comma 0. And then we have the asymptotes to be y equals plus or minus b over ax, which is plus or minus 4 over 3x. So we can plot all of this now. So I take this here. I think we're going to have a lot of interference, but let me see how it looks first before I decide to delete the previous one. So we have x squared over 9 minus y squared over 16. X squared over 9 minus y squared over 16. So we have that. And then the asymptotes, of course, will be y equals b over a. That's 4 over 3x, 4 over 3x, and then, so, you can, if you have the patience, you can actually make something beautiful out of all these, out of all these figures. You can actually make very excellent designs out of these things. So, but I think I want to let go of this. Oops, I've removed, yeah, better. So this is what we have now. So let's talk about the foci and things like that. So the center is 0, 0, of course. That's easy peasy. We have 0, comma 0. That's the red dot. Then we come again. The vertices are plus or minus 3, comma 0. Let me see if that works. If I can do backslash PM. Let me see. PM 3, 0. Okay, that doesn't work. So I'll do 3, 0 separately. That's this blue dot here. And then I do minus 3, 0, minus 3, 0. Okay, that's this green dot right here. So what else do we have? Foci plus or minus 5, 0. So that is 5, 0. That's this purple one. That's the one focus. Then minus 5, 0. That's this other one right here. What else do we have there? The asymptotes. Okay, I've already done the asymptotes. Okay, so that is how it all goes. Of course, we can switch over this axis, right? From what we learned before, we can switch over the axis. Yeah, we can switch over the axis. In this case, what we just do is to now say, instead of x, we have y, and then instead of y, we have x. So you can see it switches over like that. So we can play with these things to come out with beautiful designs. So in this case now, we have the asymptotes to be, I think it's still y. So that's y equals 3 over 4 x. They can sit an asymptote to the red one. And then we also have same thing now. All right. And then that's y minus 3 over 4x. So we have this green line there. So if you want to see that reverse one now, let's just delete all these ones. So now it's about the y-axis instead of the x-axis, like before with the asymptotes also. Okay, so example 3, we want to find the eccentricity and asymptotes of y squared over 49. So normally, you know, it should be x squared over 49. But in this case, now we have y squared over 49 minus x squared over 25 equals 1. So in this case, a squared is 49, b squared is 25. So, and the eccentricity is square root of 1 plus b squared over a squared. That's square root of 1 plus 25 over 49. That's square root of 74 over 49, which is square root of 74 over 7. That is the eccentricity. And the asymptotes are simply y equals plus or minus a over bx, not b over a anymore, because we are doing it about the y-axis. So that's plus or minus 7 over 5x. So we can plot that y squared over 49, just this, y squared over 49, then x squared minus 25, like that. So now the asymptotes will just be 7. I think it's, is it 7 now? I think it's, the asymptotes, of course, is 7 over 5, yeah? 7 over 5, like this. And then this is minus 7 over 5, like that, okay? Those are the asymptotes. So then let's talk about tangent and normal. Of course, we saw this when we're talking about chords or something like that. So tangent and normal. For the hyperbola, x squared over x squared minus y squared over b squared equals 1. The equation of tangent at x1, y1 is xx1 over a squared minus yy1 over b squared. Instead of having x squared, it's now x times the point, then yy1 all over b squared equals 1. Equation of normal now will simply be the, you have to, it's the normal is the line that is at 90 degrees to this one. So once you get this one, you can always get this one. And if you do all the rearrangement, so you get a squared over x squared x over x1 plus b squared y over y1 equals a squared plus b squared, basically. So, and that takes us to example 4, where we talk about this whole tangent thing. Okay, let me just leave it the way it was and go step by step. So find the equation of the tangent to the hyperbola x squared over 16 minus y squared over 9 equals 1 at the point 5, 3. Okay, So the standard equation, as we know, is x squared over x squared minus y squared over b squared equals 1. So comparing, we have that a squared is 16, which then a is 4. B squared is 9, which implies that b is 3. So we have 4, 3 for AB. So equation of the tangent at x1, y1, that's 5. That the x1, y1 now is 5, 3. Okay, having taken care of that, can I say equation of the tangent at x1, y1 is x1 over a squared minus y1 over b squared equals 1. So substituting x1, y1, which is 5, 3. So we just have x times 5, 5x, y times 3, 3y. So we have 5x over 16 minus 3y over 9 equals 1. So if you simplify this, okay, we simplify this. 3 cancels. 3 here is 1, 3 here is 3. So we have 5x over 16 minus y over 3 equals 1. So if you multiply through by the LCM, which is 48, 16 in 48 is 3. 3 times 5 is 15x. Then 3 in 48 is 16. 16 times y is 16y. And that's 48. So at the end of the day, the final equation of the tangent is 15x minus 16y minus 48 equals 0. So if you look at the original equation, that's 16, 9, right? 16, 9. So let's say this is 16, x squared over 16 minus, okay, now it's x squared. X squared over 16 minus y squared over 9. Okay, that's what that is. But then the tangent is the focus at the end of the day here. So that's 15x minus 16y minus 48 equals 0. 15x, 16y. 15x minus 16y, okay, minus 48 equals 0. So you can see that that's a tangent at that point. Okay, I think it's a 5, 3. 5, 3. Where is 5? Okay, I guess we have to zoom in. 15x minus 16y minus 48. And that's it. Let's see again. 5, 3, yeah? This is 5, 5. This is 1, 2, 3. Is there something wrong? Let me see. X squared minus 16 minus y squared over 9. X squared minus 16. X squared over 16 minus y squared over 9 equals 1. And this is the tangent. Okay. So, and then it cuts at these 2 points. So this is 5, 3 right here. 5, 1, 2, 3. This is 5, 3. So how come this is really not cutting? Equation of tangent at 5, 3. So 5, 3. So it should be it's not working, it's not making so much sense. What could be wrong? Yeah, I think we've done everything right. X1, that's 5x, 3y. Okay. Is that how that goes normally? Okay, I mean that's what we have. So that's it. So then we want to find the normal of find the equation of the normal to the hyperbola x squared over 25 minus y squared over 9 equals 1 at the point 10, 6. So the equation of the hyperbola, of course, standard is this. So that means a squared is 25, a is 5, b squared is 9, b is 3. The equation of the normal at x1, y1, we have that to be a squared x over x1 plus b squared over y1. That's a squared plus b squared. So a squared is 25. We have 25x. B squared is 9. That's 9y. X1 is 10. Y1 is 6. So we have 25x over 10 plus 9y over 6. And then a squared plus b squared, that's 25 plus 9. And that gives us 34. So we have 5x over 2 plus 3y over 2 equals 34. All right. So if you multiply through by 2, we get 5x plus 3y equals 68. Okay. Find the equation of normal. So that's the final equation of the normal is 5x plus 3y minus 68. So let's do that on Desmos. X squared over 20, that's 25, 9. Well, these things don't have to be perfect squares, by the way. It can be anything. So that's 25, 9. So for 25, 9 now. So for 25, 9, the normal is found to be 5x plus 3y minus 68. 5x plus 3y minus 68 equals 0. Okay, so you can see that's normal to the, it's normal, normal to the hyperbola. Okay, so let's talk about rectangular or equilateral hyperbola. So rectangular hyperbola has A equals B. So whenever A is equal to B, then you have a rectangular hyperbola. And then the equation is more or less like xy is equal to c squared. So A is simply equal to B. That's more like having something like uh 25, 25 like this. So it becomes like a rectangular hyperbola. If you multiply through by the LCM, right? So it means it becomes like x squared minus y squared equals 25. Okay? X squared minus y squared equals 25. That's what that gives. So because A is equal to B, and the equation can evaluate to xy equals c squared. Okay? Xy equals c squared. So since A is equal to B, c squared, of course, is simply square root of A squared plus B squared and all that. And the center is 0, 0. Asymptote x is 0 and y is also 0. Okay? That'll be the asymptote in that case. X is 0 and y is 0. Okay? So the eccentricity usually will be square root of 2. And then we take an example. So find the equation of the tangent and normal to the rectangular hyperbola xy equals 16. So here now we have xy equals 16. So you see that it's now rectangular like that in those corners. So you have rectangular hyperbolas like that. Xy equals 16. So we want to find the equation of the tangent and normal to the rectangle to this at 0.4, 4. So again, so for a rectangular hyperbola, xy squared equals c squared. The tangent at x1, y1 is xy1 plus yx1 equals 2c squared, right? That's when you differentiate now. So given c squared equals 16, we have c squared to be 16. So x1, y1 at 4, 4. So you have 4, this is 4, 4. So 4x plus 4y plus 4x equals 2c squared. C squared is 16 times 2, that's 32. Divide through by 4, you have x plus y equals 8. So the equation of tangent is x plus y minus 8 equals 0. Okay, so x plus y equals 8. In short, x plus y equals 8. You can see it's actually a tangent like that. Then what's the other thing? We want to find the equation of the normal to that. So talking about the equation of the normal now. So for xy equals c squared, the normal at x1, y1 has the equation y minus y1 equals, it's the whole thing about the slope. So you just need an equation that is at right angle to this other one. So in this case, we also have okay, so equation of normal again turns out to be the same. X plus y equals it. Interestingly, for this specific point, the tangent and normal coincide as 4, 4 lies symmetrically on y equals x. Okay, so the equation the normal and tangent are basically the same, and that's a serious coincidence. Okay, so let's talk about some applications of hyperbolas. Okay, astronomy. In astronomy, orbits of some comets and celestial objects are hyperbolic when they pass near stars. Okay, then you have navigation systems. Hyperbolas are used in LoRa navigation, where differences in distances from two transmitters form a hyperbola. In architecture, hyperbolic designs are used for structures like cooling towers for stability. And in physics, you have some current voltage relations and wavefronts follow hyperbolic patterns. For optics and acoustics, reflective properties of hyperbolas are applied in telescope and microphone design. Then you have some practice questions to try your hands on to be sure you really get the gist. So find the equation of the hyperbola whose foci are plus or minus 10, 0, and vertices plus or minus 6, comma 0. Determine the eccentricity and asymptotes of x squared over 25 minus y squared over 9. And, you can try your hands on all of this and see how it all goes. With this, I come to the end of this video. Let me know. Thank you for listening. Let me know how helpful this is for you. And if there's something you'd like me to try out, feel very free to let me know. So if you have subscribed already, I thank you so much. If you haven't subscribed, why not go ahead and subscribe right away? Okay? And don't forget to hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can take it a step further. You can click on join to become a member of the channel, and that comes with some special privileges. Okay? Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.